Welcome back. This is the last video about chapter 1, in which we are going to do a quick refresher on Hilbert spaces that in principle you studied in second year in details. Okay, so what is a Hilbert space? Okay, first we have to define the notion of an inner product space or a pre-Hilbert space. So an inner product or dot product over a vector space is a bilinear map which is symmetric, positive, and non-degenerate. Okay, and usually it's denoted by these symbols, two brackets separated by a comma or by a vertical bar or two parentheses. Okay, and now, so a vector space equipped with an inner product is called an inner product space or a pre-Hilbert space. Okay, now since the inner product of x by itself is non-negative, when you take its square root, we obtain a norm. So this is the norm associated with the inner product or induced by the inner product. And of course, we have to check the triangle inequality, which is less trivial than the other properties. But this is just a consequence of the Cauchy-Schwarz inequality, which states that in absolute value, the inner product of two vectors is at most the product of the norms of each vector. Okay, so the triangle inequality is just a consequence of this fundamental inequality. Okay, so now, so therefore, an inner product space is a norm space. It's a particular kind of norm spaces. And the inner product space is called a Hilbert space if it's complete with respect to the norm associated with the inner product. Okay. Now, let me give just quickly three examples. The first example is a finite dimensional Hilbert space. We can prove that a finite dimensional actually, because it's finite dimension, it's necessarily complete, as we know. So a finite dimensional Hilbert space, we can prove that it's necessarily isomorphic or isometric even to Rn with the usual inner product. Okay, so all finite finite dimensional Hilbert spaces are the same. Actually, they are isometric, as you can see. Now, an example of an infinite dimensional Hilbert space is the L2 space of all sequences such that the series with general term each component squared is convergent. Okay, this is the famous L2 space. And on this space we define the natural inner product, which is just the sum of the product of each component by each component. Okay, so this generalizes the previous example, but to an infinite sequence, to infinite sequences. So we get an inner product, and when equipped with this inner product, L2 is complete. Okay, so in principle you proved that in second year. And last example of a non-complete inner product space is just consider the space of continuous function on a compact interval AB into R, and define the inner product of these two functions by the integral of their product. Okay, so this is, as you may know, it's easy to check the properties of an inner product, but however, this space is not complete. Okay, in principle, you proved that in second year. It's not terribly difficult. Okay. And now I will end with a fundamental theorem about Hilbert spaces. Is the Riesz representation theorem, one of his representation theorems, because he has, actually they were two brothers, I think, or related, Marcel Riesz and Friedrich Riesz. I don't know to which one this theorem refers to, but there are several Riesz representation theorems. This is one of them. If you have a Hilbert space and an element in the dual of a norm space in general is the set of linear bounded operators that takes values in R. Okay, so for any element in the dual of H, there exists an element in the space A such that f of x is an inner product between A and x. And of course, then it's easily seen that if this is true, then the norm of f is the norm of A. So, of course, the proof is not trivial. It uses projections on subspaces and so on. So I will not do it. In principle, you did it in second year. But this theorem has a very important consequence, is that there is an isometry between the dual of a Hilbert space and the Hilbert space. Okay, you can write it down actually. So if you go from H to H star, to each A, you associate this. If you fix A, then as a function of x, this is an element in the dual, okay, and it's surjective by the Riesz representation theorem, and the isometry follows from this. Okay, so this is another identification theorem. We can identify. We already identified two spaces already. We identified not. There's a difference. The first result was we identified the set of bound linear map from R to E with E, where E was the norm space. And now we have another identification, and we identified also the set of bilinear maps, bilinear bounded maps with a space of linear maps into this space of linear maps. So we have so far three identification results, if you like. Okay, so this ends this short video. And so thank you for your attention. In the next video, I will start with chapter 2 about differential maps.